Hello, good afternoon, everybody. Today I'm conducting yet another experiment, technical experiment, by lecturing in the room number 6 in IMPAN. I just want to make sure that this is yet another room which is fully Zoom friendly for all purposes. I very much trust that there will be no problems whatsoever, but if there will, you have been warned. Now, before we pass to the main part of the lecture, which is to prove the theorem that we stated a week ago, I need to do two things. First, I would like to fill a gap. And secondly, I would like to recall something very important for today's lecture. So remember some time ago, we listed as an elementary fact that if you have a graph with finitely many vertices, then the relative concave algebra is unital. And it's very easy to prove because we all proved in the previous semester that the path algebra is unital if and only if you have finitely many vertices in your graph. And of course, you have exactly as many vertices in the extended graph as you have in the original graph. So the same goes for the path algebra of extended graph. And now when you go into the relative concave algebra, this is just a quotient of the path algebra of extended graph. And of course, when you take the quotient of a unital algebra by some ideal, then it's a unital algebra. So this way it's completely trivial. But now in order to prove the opposite, namely that if our relative concave algebra is unital, then necessarily easier is finite, well, we needed a basis theorem. More precisely, we needed this corollary 237, right? We needed to know in particular that whenever we restrict our paths either to paths only in E or only in E opposite, so we don't mix starred and non-starred edges, we have a pure path either in E or in E op, then chi of such a P, the class of chi of such a P is not zero. So this is stated here by saying that the canonical quotient map, when restricted to KE or KE op, is injective. Okay, that's what we need in order to prove the opposite implication, which is corollary 238. Okay, so I would like someone, because it's just an easy exercise and it's really having this corollary 237. You prove it in exactly the same way as we did this for path algebra. I would like someone to do it as an exercise, say in 2 weeks or whatever. All right, so this is the thing I wanted to recall. I know it's very elementary, but I wanted to state it for the record because it's when we will be dealing with categories of relative concave algebras, I wanted to be crystal clear that whether I say, okay, it's a category where graphs have finitely many vertices, or it's a category where we have unital relative concave algebras. That's the same thing. This is the same restriction. Okay, now what I want to recall for today's proof is something on page 60. I hope I can scroll it a bit faster. Okay, 66, 63, 62, 60. Well, yes, we will be using this lemma extensively today, right? This is a lemma which tells us about the contravariant covariance of the path algebra construction. So this is exactly what you have here. This is our F star. And actually, you know, what is really important, the key thing is this formula. So now we see why, in order to talk about this contravariant functor, we must assume that our maps are proper. Otherwise, this expression wouldn't make sense. Okay. And now, and this is what I want to stress, because this is a key difference between what we proved thus far about the functoriality of a relative concave algebra or Leavitt path algebra construction. Namely, we really have to assume that we are in the category of graph morphisms, not path morphisms of graphs, but graph morphisms. So this means that our map F from finite paths to finite paths respects the lengths. Or in other words, not only you map vertices to vertices, but also you map edges to edges. You must not map edges to paths of which are not edges. So we cannot shrink You cannot shrink a loop to a point, and you cannot map an edge to a path, say, of length 2. Okay, so that's forbidden, and I want to show you why. And this transpires in the proof of this lemma at exactly this place. Yeah, I will highlight it. Okay, so we are trying to prove, we know that we have a well-defined linear map. This is no-brainer, but now a key thing is to prove that this linear map is in fact an algebra homomorphism. And to this end, we take basis elements in our algebra and we multiply them and we see if they come out all right. Well, they do. See, f star of chi p chi q is equal to f star of chi p times f star of chi q. So we are home and dry. But I wanted to alert you to the place at which the magic happens, at which we use this assumption that f preserves the length of paths. Okay. And I think it happens right here for this equality. Okay. So we are looking at a composed path, PQ. Okay, just to focus attention, of course, we should study separately the case where the end of P is not equal to the beginning of Q, so everything should be 0, but this is really trivial. So for the sake of the argument and just to focus attention, let me assume that TF of P is equal to SF of Q. So this Kroneker's delta is just 1, and I really have a path here, okay? So PQ concatenates the path. All right, and then you see in general, if I have that PQ is a path, well, I cannot just claim that the preimage of this path decomposes. See, I can give you a very simple example. For instance, let me do the following. I have one graph which has simply 2 edges and 3 vertices, okay? And I have another graph which has just 1 edge and 2 vertices. Okay, so you can imagine a path homomorphism of graphs which maps the first vertex to the first vertex. It maps the second vertex nowhere, and it maps the second vertex to the second vertex here. All right. And now you can say, well, I think I did it the other way around. Sorry. The map goes the other way around. I'm mapping this graph to that graph. All right. So V0 goes to V0, V2 goes to V2, V1 is not in the image. And of course, now I have basically no choice. My edge E from V0 to V2, okay, f of E must be the path. Let's call it E1, E2. Okay, otherwise it wouldn't be path homomorphism of graphs. Okay, so it's of course a proper path homomorphism of graphs, but why wouldn't it work? Okay, let's look at the formula. We would like to compute this expression. So we would like to compute f star of chi E1, chi E2. Well, here that's something simple because this is just f star of chi E1, E2, right? And I keep on computing, and now I look at the preimage of this path E1, E2. And well, it gives me just edge E. So this will be chi E. There is no sum. Okay, but now let me compute the other expression. So I computed the top. Now let me compute the bottom. So f star of E1 times f star of E2. But you see, by this formula, well, I'm just looking for all paths which are in the preimage of E1 and in the preimage of E2. But these are empty sets. So this is just 0 times 0. Okay. And this does not agree because chi e is not 0. So this means that here we do not have equality. All right. So this is a very, very simple, very trivial example, which shows you that indeed we better assume that f preserves the length of paths. So this is really a graph homomorphism, not just path homomorphism of graphs. All right. Okay. But now in the next thing I want to point to you. So first let me erase. Let's see if I can do it efficiently. Okay. Now to tell you why having f preserving the length of paths does the job. I know we explained it in the previous semester, but many of you did not attend in the previous semester. And also this is very important to appreciate an assumption. I don't want you to think that I make my assumptions at random. I do my best to justify making them. Okay, I think I managed to erase everything. Great. All right, so yes. Now, if you assume that the length of path is preserved, okay, and you have a path R, oops, I have to choose a pen. You have a path R such that FR is equal to PQ, all right, so that's exactly this condition. Well, then because the path is preserved, it's clear that there must exist R1 and R2 such that R is equal to R1 times R2 and f of R1 is equal to P, f of R2 is equal to Q. So that's what we've got when the length is preserved, all right? Otherwise, this equality wouldn't hold. So this is why, and now I can make this third step. Because I can say, well, I'm not just looking at all R's in the preimage of PQ. I'm looking at all R1s in the preimage of P and all R2s in the preimage of Q that concatenates to a path. So here I have this Kroneker's delta. And then I have a chi R1, R2. And then the rest works immediately because you write it as multiplication of two sums and you're home and dry, all right? So that's why here, unlike in the covariant case, where until the end, until having the Levitt path algebras, we proved the functoriality for Levitt path algebras under path homomorphism of graphs, of course, satisfying zillions of conditions, but not necessarily the condition of being graph homomorphism. And we even remember we studied a very particular example where we had a graph which was just one loop, and we mapped it to a graph which is just one point. So this definitely did not preserve the length of a path. And it yielded a very nice and important homomorphism of algebras. Okay. But here we don't have this luxury. And well, sorry, it was actually, in a way, it's a luxury. In a way, it's a nuisance. It's a luxury because now when we have stronger assumptions, our computations are easier, right? I mean, it's always easier to handle graph homomorphisms than something more general like path homomorphism of graphs. But on the other hand, it's a nuisance because it kills some examples that you would like to keep. And I think that's all I need. Actually, I can kill this now. That's all I need from here. So I stop sharing. Yes, I now can minimize this and I will start sharing again. But now whiteboard. And move it on the right screen. Maximize. Yes, I think now it works. And my pen is fixed. Let me just change the color to brown. And now it should work. Okay, so basically the theorem that we wanted to prove was the following, that if I define my f star, oh, sorry, this is the wrong, wait a second. Yes, I'm sorry. Yes, everything is fine. I forgot that the previous theorem was still covariant. Sorry. That's this recall I made for you because I didn't want to switch my screens twice. It was because after we are done with the proof of this covariant theorem, we will go to a contravariant lemma. And for the contravariant lemma, done for just conpav algebras to begin with, I will need this lemma that I recalled. So sorry, this is why I was confused. Okay, so that's still a covariant construction, and we start from a graph path homomorphism of graphs satisfying a number of conditions. So this was R M I P G. RMIPG. It's very important to remember when you write on Zoom's whiteboard not to go all the way to the top of the screen because this has some different functionality, but it's invisible because it's white on white. Okay, so we simply take morphisms in this category. Objects are just all graphs. Okay. So we have an F here, and this means what? It's a path homomorphism of graphs, which is injected on vertices, satisfies the M condition and the regularity condition. I'm not going to go back to what they are. You'll see them at work during the proof. And this is and again I touched the top. This is a map from. Well, this is a path homomorphism of graphs, say, going from E to F. Okay, and we want to assign to it, this is what a functor does, F star L.
I cannot see anything.
Which is now, well, I'm running out of space, so let me write it right here. F star L is a map from, yes?
I don't see writing. I'm not sure if it's my problem or.
Oh, you don't see me writing? Okay, so let me. The only thing I can do. So thank you for telling me. I can stop sharing and start sharing again. Whiteboard. Share. Can you see the writing now?
Yes.
Okay. Yeah. Thank you so much for. Noting it, because I don't know what you see and what you don't. Okay. Yeah, but let me clear it anyway, because I wrote it in a very big way. But let me be a little bit more succinct because we already stated this theorem, so I don't want to talk too much about it. The key formula is the following, that given a morphism of graphs satisfying a number of properties given by so many letters, I simply can construct a unital homomorphism of algebras. And the formula is very simple. I simply take a chi p, the class of chi p, which is an element in the Leavitt path algebra of my graph E, and I map it by this homomorphism to B, by the assignment where I want to prove that it's a functorially defined homomorphism of algebras. I denote it by F star of L, or F star L if you want. So this is mapped to chi F bar of P. Oh, now remember that chi P is an element of the path algebra of the extended graph. Okay, so I have to apply this F bar here. And that's it. This is the definition. And this class is in the Leavitt path algebra of the graph F. Okay. So we have to prove that this is well defined. We have to prove that, well, we don't have to prove it. If we prove it, look, when we prove it, this is well defined, it's obvious an algebra homomorphism, okay? Because if you see, we know that F bar is an algebra homomorphism. Sorry, what am I saying? We know that F star is an algebra homomorphism. So if I go by F star from the Leavitt, from the path algebra of extended graph Ke bar to the path algebra of extended graph F bar, I already know that this is a path homomorphism. This is a homomorphism of algebra. Sorry, we already know it is a homo of algebras. That will be proved in the previous semester. Okay. So now the name of the game is that we go to the quotient, we divide it by the ideal, and this is my Leavitt path algebra LKE. This is my Leavitt path algebra LKF. Okay, we go to the quotient, and we want to make sure that this induces a map here. Well, which is by saying that this F star L is well defined, and this induces a map down there. If and only if this F star maps the defining ideal in Ke bar into the defining ideal in Kf bar. But when we check that this is the case, then not only we know that this map F star L is well defined, but also it's naturally by construction an algebra homomorphism. Because if an algebra homomorphism quotients to a quotient algebra, then it's of course also an algebra homomorphism. So this doesn't have to be checked. And then we just have to check the functoriality, which is trivial, and then we also have to handle unitality, which again is trivial. So basically, roughly speaking, all that we need to do is just to verify that F star induces F star L, or in other words, that the ideal is mapped into the ideal by F lower star. Okay, so now. Well, here there was one more step because we in fact had it proved. Sorry, I should have here the bar. We know it without the extended graphs, but then we had this lemma which Niklas proved that if F is IPG, then F bar is IPG. That's why I can claim that this F bar star is the homomorphism of algebras. Because the lemma was proven under the assumption that if I have a graph homomorphism, which is a path homomorphism of graphs, which is IPG, that it deduces algebra homomorphism between the corresponding path algebras. Okay, so this is what we want to prove, and that's what I want to compute. But now I want to use here something that Majid was explaining in the recitation class. Notably that if I have sort of the following double construction, I take A, I divide it by the ideal, but then inside here I take some ideal and I divide it one more time. Okay, when roughly speaking, what I'm doing is just I'm dividing A by I plus J. Okay, we discussed it at length during the recitation class. Why do I need it? Because you see here I told you that the Leavitt path algebras are quotients of path algebras of extended graphs. Of course it's true, but we have a subquotient on the way. You see, I can here I need the eraser. Okay, in between I can put the absolute conpath algebra. That's an in-between quotient. And we already know that here this works. So in fact, instead of really proving that F bar star maps the defining ideal into the defining ideal, we can just look at F star C, okay, and here prove that it maps the defining ideal into the defining ideal. This means that we will not have to check the first Conspicuous relation, we'll only have to check the second Conspicuous relation, okay? So that's sort of a hierarchy of concepts. This is what's going on. That's what we have to verify. And now just let's do it. So I start the proof. And after all this explanation, I can say so following the proposition proved a week ago, it suffices to verify that for any regular vertex V, the following is true. If I take the sum over all edges in the preimage of V, and here I'll have chi F bar E star, then this is just the same as the class of chi of F bar of V. Okay, remember the second Conspicuous relation happens only at regular vertices, so that's all that we have to verify. And to check that the defining ideal is mapping to the defining ideal, we have to check this equality. Because now if you want, I can put this chi of F bar of V on the left-hand side, I can put it inside the class, and I'll have 0 on the right-hand side. I can also put sum into the class. And this is these are generators of my ideals, and they have to vanish when I map them on to the right-hand side, and then I take the equivalence class. All right. So this is precisely what we are doing, and this is what we have to compute. All right. So that's to be checked. Now, to this end, we need to apply the regularity conditions. Of course, we need to apply. This was quite a complicated condition. I think the first assumption was that we map irregular vertices to regular vertices. That's important. And then we had a very specific condition as to what happens between the edges originating at F of V and edges originating at V, all right? So there was a very, very specific and tricky construction on how to do it. And we're going to use it right now. I will recall it on the go. I don't want to bore you to death and go back and then again repeat definition. No, I mean, we did it a week ago, and you have it in the lecture notes. So I hope this definition will come back to you once you see me using it in the proof, okay? So now, okay, let's compute it. And I say here that for starters, by the projectivity assumption, okay, so here make, okay, yes, the projectivity assumption says that if I look at all edges emitted at my irregular vertex V, okay, so this is one set. On the other side, I have a set of paths. I denoted it by FPV, so this notation is important. This is the set of paths which are in the image of a map F. Okay, and I want this, when I restrict to the preimage, I want this to be bijective. So this is the bijectivity condition, right? So these are paths, of course, starting at FV. So now we see that this vertex f of v must be regular, because if it emitted infinitely many edges, then it wouldn't satisfy the second part of the regularity condition. But anyway, this is one of our assumptions. It's that f of v is also regular. Okay, so these are paths, not edges. These are paths starting at f of v, and these paths are in bijection with all edges, the set of all edges starting at v, in bijection via f. But moreover, most importantly, this set FPV is constructed inductively in a very specific way. All right. So this was the tough part, was to find this condition, and I'm going to apply it right now. I'll remind you this condition on the dot. Okay, but let's do it in some order. So for starters, by the bijectivity assumption, which I just explained, we have the following. When I take the sum, so I'm basically computing the left-hand side, all right? So I have the sum over E running the preimage of V. And here I have the class of chi of F bar of E star. Okay. Now, what I do, I know that F bar of E star is F bar of E, F bar of E star, which is F of E, F of E star. And then I multiply the chi's. So I'm doing basically nothing here, just the trivialities. I sum over the same set. And here I have the class of chi F of E times the class of chi Fe star. Okay, so that's immediate by definition. But now, because of bijectivity, I can say, aha, this is the same as the sum over all paths Pi. I don't know why I noted them with an I. Okay, let me keep the subscript. I think it's redundant, but let me keep the subscript. Otherwise, I'll get confused with my notes. But I think I overdid it. I don't write EI running a set. I write E running the set. So I might as well write P running the set. Okay, let me try. If maybe I will not get confused. I mean, it's nothing important, just notation. But I realized that I was writing an additional I, which was not running index. I'm already running P's, so why bother with I? Okay, so now I have paths running this set FPV. And of course, here I have the same. So it's chi, because you see, of course, this is a bijection, all right, so from this set of, which is the preimage of V to FPV. And of course, when you apply this bijection F, you turn E into P. So F of E is P if you want. So now this is chi P times chi P star. Okay, right. And here comes really the crucial part I'm very happy about. In order to handle this calculation further, so continue writing what it is equal to, I need to somehow partition my sets into subsets, into some layers, and I realized that the best way to decompose it into disjoint layers is by taking lengths of the paths. Okay, when you say that your path is of a given length, okay, then it cannot be of any other length. So paths of different lengths are simply different paths. Okay, so that's what I'm going to use. Of course, since we are talking finite sets, remember V is regular, F of V is regular, and therefore all the sets in question here are finite. So I can choose a number n, which is the length of a longest path. So next, let n be the length of a longest path. And it's important, this article here, it's a longest path. You can have many paths with maximal length, which are different. There's no like the longest path in general, of course. Okay, so a longest path in FPV. So these are the special paths in the special constructed subset of FP F bar. Then we can partition FPV by path lengths to obtain the following. Now I write that sum over P in FPV. And here I have the class of chi P times the class of chi P star. Yes, but now I'm writing it, and now this running index makes sense. I call it J. So J ranges from 1 to n. I'm wondering. Yes. Okay. Okay. That's in this regularity condition. When we have our f not necessarily preserving the length of the paths, it does not necessarily mean that f of the edge is longer than an edge that is of length 2 or more. It can also be of length 0, and this was in our example, which we studied. But here the regularity condition prohibits it, right? If you look as to what happens into the construction of FPV, its elements are paths of length at least 1. These are positive length paths in FPV. Okay, this is why I start my sum from j equal 1, not from j equal 0. But that's assumed. That's by construction. It's not that we necessarily must have that f of an edge is longer than an edge or equal to an edge, or it can also be a vertex, but that's excluded here by the regularity condition. Okay, so I have a sum from j equal 1 to n, that's the longest length. And now, of course, what we do, we have the sum over p's over, say, pj's, and now I need this index. And this runs FPV intersected with FPJ, where FPJ is by definition the set of all finite paths of length j. Okay, so take all paths from this specially constructed set FPV, but only those of a fixed length j. And length j can vary from 1, so we are talking edges, to n, which is a longest path. And of course, I still have to write it down, what I have here in the sum. So it's chi p j, chi p j star. Yes, and here I already had double index, which was completely redundant, I think. Okay, so now we continue this calculation. And now I'm using Well, I mean, this is just this is very simple. I'm separating the case j equal n from the rest. So I have a sum from j equal 1 to n minus 1. And here everything else remains as before, plus just the sum over pn's running all paths in FPV of length n. Okay, so it's chi pn star, of course, classes. And I did this split because now I can compute. I can compute this right term. And how do I compute it? Well, remember the construction of FPV. Okay, if I have a longest path, it was obtained the following. Okay, maybe let me just draw a picture of how we are doing it. This is our vertex FV. When I take all edges as a regular vertex, I take all edges starting in FV. Some of them I leave them be as they are, other I extend. But the rule of extension is that I extend them by all edges that come from this vertex. And again, this is part of the assumption that these paths go only for regular vertices. So these assumptions were quite complicated, okay? And now this gives me a bunch of paths of length 2. So here I have elements which are of length 1. So this is FP1. This is FP2. Well, not quite, because some of them, again, some of them I let them be. Say all of these paths I let them be, and they remain in FP2. But this path I extend, and again I extend it by all possible edges starting over there. And this will give me FP3, and so on and so forth. So when I come to paths of length n, they were created from the previously created paths of length n minus 1, but only those that were extended. And let me then write it down. So each such a Pn, I can write it down as a path. Let me use Q. Yeah, I'll write it as Q n minus 1, and then an edge xn. So here Q n minus 1 is a path of length n minus 1, and xn, it's just an edge. We are in F. So that's in F1. Okay. Yeah, I can always do it because I know that these paths Pn come from paths Qn minus 1, which I get by the construction I just described to you. But you see, I cannot write down that Qn minus 1 run FPV. Well, no, this is not true, because in fact, these paths are not in FPV because they have been extended. They're colleagues of length n minus 1, which were not extended, are in FPV. But these guys are precisely the guys that were extended to paths of length n, so they are not in FPV. Their extensions are in FPV. Okay. All right, but then I can continue. I can now compute, if you want, this right term. So let me maybe erase my beautiful picture. Yeah, I know it's a little bit complicated to explain, but I think it is clear how we do it. If you have any questions, please fire at will. Okay, so now I compute this right term. So I have a sum over Pn running FPV intersect FPn. And now I'm going to use this notation, all right? which allows me to write it down in the following way. Okay, I still have to write this chi pn star. Okay, remember the rules of extensions. Once I fix my subpath of length n-1, which I call qn-1, once I call it, once I extend it, but all edges that can extend qn-1, right? So this is equal to the sum, and I'll explain here if there's a certain subset that qn-1 is running. I call it, how do I call it? I call it EVN-1. EVN-1. It's E not for the graph E, it's E for extensions. So these are the guys that I got in my constructions of FPV in my n-1st iteration. So I have these paths of length n-1. Okay, so here I arrived at all paths of length n-1. And again, some of them I let them be. And then these are denoted as Pn-1. But some others I extend. I denote them by Qn-1. Okay, so that's the set of all paths which I obtain in my construction in FPV that I extend to paths of length n. Okay, and all right, so this is the first sum, and then the second sum. I have to erase it. And now the second sum is, of course, over all xn's that originate at the end of qn-1. Sorry, I should use t. And this is in f. Okay. So tf minus. No, sorry, that's stupid. I'm sorry. I take the end of my path qn-1, it's a vertex. And now I take the preimage. Under the source map of this vertex. Okay, now it's correct. Right, all edges xn that originate at the end of path qn-1. But now I can write down this expression chi pn star in the following way. Of course, this will just give me chi qn-1 chi xn star and chi qn-1 star. Okay, so now we see the magic which happens here. So for starters, you can take these external things outside because they do not depend on xn. So I have the sum over qn-1, and I explained to you what I mean by the set EV-n-1. So I come to this iteration in the construction of nth iteration, my construction of FPV, and I have one subset of paths of length n-1, which I let them be, and another set which I extend by to paths of length n, and all these paths that get an extension, that get promoted longer paths, I denote by EV-n-1. Okay. All right. So that's now well defined and explained. And here I have chi qn-1. And now in parentheses, I have the sum over all xn's which originate at the end of qn-1. And here I have a class of chi xn times the class of chi, of chi xn star. I close the parenthesis, And here I have chi qn minus 1 star, of course, the classic. But you see the beauty of this construction now, because we go for each qn minus 1 fixed, we go over all xn's that extend that, okay? Then this means that what we have here by our second Kunstkrieger relation in the Levitt-Pav algebra of F, well, we just know that this is equal to this whole middle sum is equal to nothing but the class of what? Of the source of these edges, which is the end of qn minus 1. So it's chi tf of qn minus 1. But of course, it's being absorbed. So chi qn minus 1 times chi tf qn minus 1 is, of course, just chi qn minus 1. That happens already at the level of path algebras. So that's being absorbed. So this means that we can completely vanish the middle term. Okay, so I'm now having these paths of length n minus 1 running the set EV n minus 1. But look, here I have other parts of my sum. So in particular here now I can take j equal to n minus 1. Okay. So then I have all paths of length n minus 1 that are in FPV, and all these paths that would be in FPV if I didn't extend them to paths of length n. And I add the whole expression. So now let me write it down. Now I'm basically is making an inductive step, if you want. Okay, let me write down this. I'm wondering whether I should write all that stuff. Maybe it's good, because if someone has visual memory as I do, I cannot remember things that are said to me. I can only remember things that I see. I mean, it's much easier for me to remember. So okay, let me write down what I told you. So here E Vn minus 1 stands for all paths of length n minus 1 that were extended to paths of length n in the construction of FPV. Okay. So furthermore, combining a just defined set EV n minus 1 and FPV intersected with FP n minus 1, we obtain all paths of length n minus 1 that were obtained in the construction of FPV. By extending paths of length n-2, by extending by all possible edges. Okay. So we are back to where we were before, but with an index n and now lowered to n-1. So what used to be n and n-1 now is n-1 and n-2, but the phrase is exactly the same. So when I combine these two sets, and that's exactly what I'm doing, I'm grouping together all paths of length n-2 in my two sums. Then I see that indeed, when I group these paths of length n-2, then I obtain all paths of length n-2 that are obtained in the construction of PV by extending paths of length n-2 by all possible edges, right? Because all such paths are paths that either are paths that are left alone or the paths that are extended, and we have them all together, so we have all of them. Okay. So now I can repeat my construction. Okay. So that's completely analogous, and well, let me just write down that hence we can iterate the above calculation. And now look what it does to us. I take the sum over all paths of my highest length. I compute. And as a result of this computation, I drop to the case where I have no longer paths of length n. My longest paths are of length n-1. And again, I take them aside. So I take all these paths of length n-1. I repeat this construction. This way I remove all the sum over paths of length n-1. I drop down and down and down. And because n is finite, at the end of the day, I'll have simply my index equal to 1. Okay. And the sum which I will obtain will be something very simple and desirable. So by iterating, right, we conclude the following. So we can iterate, and we do iterate. So iterating this calculation, sorry. We conclude that what we started from, which was this sum over all elements of FPV, and have a class of chi p times a class of chi p star. Well, we will end up simply with a sum over all Q1s, which are all edges emitted at f of v, our root vertex, if you will. And here we'll have what? Chi, the class of chi q1 times the chi of chi q1 star. But because it's the sum over all of them, remember, this is how we constructed FPV. Well, this is nothing but the class of chi fv. And that's exactly what we want, because now if you look to the right-hand side of what we are computing, well, you know that f bar of v is just f of v, right? I can just write down here chi fv. So we are done. Well, almost. You still have to argue about factoriality, but this is it's done exactly the same way as before. You know, in our previous week argument for the factoriality of this construction, we replace the letter C by the letter L, and everything else is identical. So that if you have a factorial construction and it descends to a quotient, it remains a factorial construction. It's very easy to check, and we did it before for conv algebras, and now it's exactly the same for the Leibniz path algebras. So let me skip it. And well, there is also some unitality issue, I think. Let me check. Yes, okay. So let me write it down like this. So finally, the covariant factoriality is obvious. And assuming that for graphs with finitely many vertices, F is bijective on vertices, we also obtain the unitality of F star L. Well, that comes immediately from the claim we have for conv algebra. It's either the same argument or you say if a unital homomorphism of algebras goes to the quotient, then the quotient algebras are also unital, and with induced homomorphism that descends to the quotient is also unital. It's trivial. Let me not write it down. I'll put the full stop here, unless you have a question, but I don't think so. Okay, so, oh my goodness, we have only half an hour left, and it's only now that we finish the proof of a theorem from the previous lecture. Now we are going to move into the contravariant realm. So if you still have any questions about the covariant realm, covariant factoriality, that's the highest time to ask them. I like this theorem, not because of its proof, because there is no surprise here, but in fact, in order to cook up this proof, we had to cook up the condition. And as I told you already a week ago, that's something I'm very happy with, because this is I believe, not such an obvious condition. Of course, it's obvious from a hindsight. Now it seems obvious to me, but it wasn't obvious to me when I was thinking about it. Historically speaking, this theorem which we just proved is a very, very extensive, significant realization of a lemma you have in the book of Leibniz path algebras. So you see, you have such a lemma in the book on Leibniz path algebras, which says that if you have a graph homomorphism, morphism of graphs, okay, not path homomorphism of graphs, but graph homomorphisms. So this is a strong assumption which we do not have here. We will have it in a second because we will do the contravariant construction, but in the covariant construction, we do not assume it, okay? Then you realize that the lemma which is written in there is very special case, it's very simple-minded. Then we extended it with Mariusz Tobolski and Alex Kirvasitu to something stronger. And we proved that again, such a covariant construction works. We have a functor into Leavitt path algebras, and this functor induces out of path homomorphism of graphs satisfying a bunch of conditions, homomorphism of Leavitt path algebras. But here we go even further because, as I told you before, the M condition, I was explaining it to you on examples, the M condition is something weaker, something more general than we assumed in our paper. And remember, this M condition was that if f of an edge is less than equal than f of another edge, then these edges are equal. That's not the same as having and edges being equal. It's the same as edging being less or equal to E prime. That's equivalent. But now, if you think about E and E prime not as edges but as paths, of course, for paths it's no longer true that equality is equal to inequality, but for edges it is true. If you want to extend it from edges to paths, you get a stronger condition, which is not necessary. Okay. So now I think that this is like the end of the game. I don't think you can generalize it any further in the realm of path homomorphism of graphs. I believe that this is the ultimate generality one can get in order to claim that from a certain path homomorphism of graphs, we induce functorially in a covariant fashion a homomorphism of the induced the respective Leavitt path algebras. Okay. So result in our paper improved a result in the book, and this result just proved to you improves the result in our recent paper. Okay, are you ready for the contravariant world? I hope so. So for starters, I need to introduce a certain target bijectivity condition. So we go to the contravariant construction. And that's a formula which I was recalling at the beginning of my lecture, right? If you go from E to F, now we go from K F bar to K E bar, okay? And you do it by taking pre-images. So chi P is mapped to the sum over all Q's, which are in the preimage of F bar, which have a preimage of an F of P. So in other words, F bar of Q is equal to P. And here we need to have a properness. And again, Niklas was proving that if F is proper, then F bar is also proper. So this all makes sense, okay? So that's this construction. But it's very easy to see that this is contravariant. Okay, and now let me define a certain condition under which I can prove that such an assignment gives me a factor, but now between the con path algebras, not just path algebras, but con path algebras. So we want to see that this map, or if this is F, I denote this by F, say F bar star, upper star, because it's contravariant. Now I want to make sure that it will go to what I will denote as F star C. I go to the quotient, and here I have the con path algebra of F, and here I have a con path algebra of E. Okay, I want to prove that this induces a quotient map, where that's my formula for F bar star. All right, so in order to prove that it works, I have to assume certain condition. I will wrap it up in a definition. Well, for the lack of a better name, I call it target bijectivity, but I'm not religious about it. If you have a better name, please let me know. Well, this condition is far more obvious when you try to prove this lemma than the regularity condition that we used in the proof of a just explained theorem. But its formulation, again, was not so completely obvious, but I think the formulation I'm going to give to you right now is optimal. Okay, so when do we say that we have this target bijectivity? So we say that morphism F from E to F. Well, let's assume that this is the proper morphism of graphs. Okay, so POG. Well, of course, I could say, and that we can define it in higher generality, but why bother? I mean, we don't want to, this is so-called Occam razor. I don't want to create some things that I don't need. So let me view this definition as a condition in this category of POG, because this is our playground. We cannot go beyond it anyway for this construction. For obvious reasons. So why bother going to other things? Although formally speaking, probably it makes perfect sense, but I'm doing it only because I don't see any motivation. It's like in many places, for instance, when people study Hopf algebras, typically, well, when you say Hopf algebra, typically when you say an algebra, you mean an algebra over some ground field, not the commutative ring. But in very, very many applications, nobody can stop you by saying, well, let's consider algebras not over fields, but over commutative rings. And then you realize that many claims that you had about Hopf algebras considered over a field are true for Hopf algebras considered over a commutative ring, provided that everything you consider is faithfully flat as a module over this commutative ring. So if you are motivated to do such things, why not? But remember that generalizing just for the sake of generalizing is hardly ever a good idea. Although on the other hand, you know, like in the Bourbaki style, if you want to understand why certain things work, you have to distill the minimal assumptions that allow it to work. And that's in a sense what we are doing, except that here pushing the generality in this direction, it's exactly what we are interested in. This is quite an unexplored terrain. That's why every week I'm proving to you a new result. The result I'm about to state, at least probably not proved today, but at least state, is also new. It's been proven yesterday. And it's not because I'm spouting some brilliant mathematics every week. It's because we simply ventured into unknown territory. And when you already land in some undiscovered country, every step you make means that you can put a flag, said, I'm first here. This mountain is Mount Kosciuszko. This mountain is Strzelecki Mountain, whatever. We can claim it because we are the first there. But this is not a difficult terrain. This is, you know, basically flat, and we are just walking, and we are jumping from one new stone to another new stone. So that's the picture I want you to have in mind. All right, so I'm so talkative. Now I just want to give you this condition. So we say that such a morphism from POG satisfies, well, maybe let me rephrase it. let. Okay, let F be a such a morphism. The target bijectivity condition for F is as follows. For every x, and I do not, now x is in F1, for every x in F1, for every edge in the graph F, when I take the preimage, the preimage under F of this edge, and now mind you, because F preserves the length and X is an edge, anything in the preimage of an edge must be an edge. Okay, so E is an edge. And now I have a very obvious map over here. Namely, I can just take the endpoint. E is in graph E, so I can take the endpoint in graph E of this edge, known as a vertex, TE of E. Okay, and of course, you can see that it belongs to the preimage under F of the vertex, which is the end of X. Right, I hope it's obvious that this is well defined. So TE of E is in F preimage of TF of X, if and only if F of TE of E is equal to TF of X. But remember that F is a graph homomorphism, so this is TF of F of E, but F of E is of course X, so they're equal, okay? So this is obviously well defined. So the target map, as I wrote it with such specific domain and codomain, is well defined and must be bijective. So the target bijectivity condition for F is that for any X in F1, this map is bijective. Okay. So that's why I call it the target bijectivity condition. But if you have a better name, just let me know. And one obvious remark that note that the bijectivity of F implies the target bijectivity of F. Of course, not the other way around, but we'll do examples later on. Yeah, I hope that this is clear, because you see, when F is bijective, both sets here are one element sets. So of course, when you have a well-defined map between two one element sets, it can hardly ever fail to be bijective, okay? And the other way around is not true, but you'll see it in examples. Also note that injectivity of F is not enough, because it might happen that if all that you assume is injectivity, it might happen that the preimage of X is just the empty set. So it might be that the right-hand side is non-empty and the left-hand side is empty. And then again, it's very hard to have a bijection between the empty set and non-empty set. Okay, so much for the obvious. Now notation. As you can guess, the subcategory of POG whose morphisms amorphisms satisfying the target bijectivity condition is denoted by TBPOG. Sorry for creating such monsters, but I have no better idea how to do it, okay? So now with this at hand, we can, in the remaining 9 minutes, at least state our lemma. It's kind of unfortunate, but I end my lecture with a statement of a complicated claim, and then I prove it next week, because then in order to start my proof, I have to recall the formulation, which is a bit of a waste of time. But I cannot help it. I mean, it would be even worse to try to prove it now, although the proof is not so long. It's half a page, but yeah, okay, let's first formulate. Okay, and now let's take the shape of the following lemma. The assignment now I take objects in my category T, B, P, O, G. So these are all graphs. Any graph is an object in this category. Remember, we restrict only morphisms. We do not restrict graphs. I assign to it its absolute concav algebra CKE. So of course, it's an object in KA. Algebras over a fixed field K. And now the interesting thing happens, of course, for morphisms. TBPOG. Okay, and I take it as F from E to F, and what I assign to it, well, now you see the contravariance, we go from CKF to CKE by F star C. And now I claim that this is a morphism in the category of algebras over K. But of course, I have to define for you this F star C. And the definition is the following. I take an arbitrary element in CKF. Well, I take an element, typical element in CKF, and other element is a finite linear combination of such elements. So I basically choose any path P in the extended graph of F. I take chi of this P, and I take this con path algebraic class of this element in my path algebra of extended graph. And by definition, I map it into the sum, well, not surprisingly, over all Q's that are in the preimage of P. Okay, and here I have chi Q. And now these classes are in the con path algebra of the graph E. So CKE. Okay, so this assignment defines a contravariant functor. Well, furthermore, that's the unitality now, right? Furthermore, the same assignment restricted to the subcategory of graphs with finitely many vertices. So you see, so this time, and that's a big difference between the covariant and contravariant construction. In the covariant case, not only we restricted graphs to graphs with finitely many vertices, but also we restricted our IPG category to BPG category. So now we demanded that not only we are injective on vertices, but we are bijective on vertices. Okay, here we don't have to do it. Definitely, we do not need bijectivity on vertices. It's not at all needed. This properness suffices. It does the job. The only thing that we need is that we restrict to get to the subcategory. We just restrict our objects. We do not change the morphisms. We are still in this TBPOG case, but now we restrict the class of objects. Okay, so the same time restricted to the subcategory of graphs with finitely many vertices yields a contravariant functor to the category UKA. Yields a contravariant functor to the category UKA. So unital algebras over the field K. So then we take the same way defined map F star C, where we prove that this is a homomorphism of algebras, that this is factorial. And now we take the unit in our conv algebra, and we know what it is. It's given by the sum of chi v, where v runs the set of all vertices. The sum is finite because we have only finitely many vertices. That's the unit in our conv algebra. Yeah, and we know it because this is obvious fact. We said that whenever a graph has finitely many vertices, then the conv algebra is trivially unital, and the unit is given by the sum I just spelled out for you. But this is why I got motivated to go the other way around. I mean, what if I decided to say, okay, let it be subcategories such that it yields unital conv algebra? So what on earth is this? Well, I mean, it's very simple. These are just all, this is a category given by all graphs which has finitely many vertices. There's no way around. I mean, you cannot have something more general. It is impossible to have conv algebra, which is unital, and it's a conv algebra. It's the conv algebra of a graph of infinitely many vertices. That's impossible, and this will be an exercise for someone to prove next week. And yeah, as I imagined, I don't have enough time to prove it. This we will do next week. So maybe in the remaining 2 minutes of this lecture, let me draw your attention to the fact how it differs from the lemma which I recalled to you at the beginning of the lecture. Okay. And the difference is very, very simple. So now I'm going to do some erasing. So that's what we are going to prove next week. But what we proved previous semester was the following. I can use the same word. In fact, when I'm typing my lecture notes, I just do copy and paste and then I modify. So what do I have to modify? I remove this target bijectivity condition. Here, instead of CKE, I take I take just the path algebra of E, and I do it everywhere. Okay, F, KF, KE. And here I can get rid of equivalence classes. I mean the path algebra. Yes, it's easier to erase than write. Okay, so this was the lemma, and this I also should, oh, I'm so sorry, you see. I didn't do it quite carefully. Yes, so now, yes, and this TB is gone. And I have KF here. All right, so that's precisely on the nose, the lemma that we had before. But now, because of this lemma which Niklas proved, I might as well bar it everywhere. So I can go from E to the path algebra of extended graph, KE bar. And when I have a morphism from E to F, I know I have an F bar morphism from E bar to F bar, which is again in POG. So this makes perfect sense. I can write here F bar star. And this is from KF bar to KE bar. Okay, so now this is KF bar, this is F bar star, this is again F bar, and this is KE bar. And the same is true by the lemma that Niklas proved, by the functoriality of extended graph construction. Of course, here the functoriality is covariant, but if you compose a covariant functor, the contravariant functor, of course you get a contravariant functor. And so that's what we have already from the previous semester. And now the name of the game is to prove that yes, that this functor goes to the quotient. But this is yet another story. This is for the next week. Let me stop sharing and stop recording.